And so we find ourselves on page 184 with the penultimate bit of subject matter for this unit. We've been dealing with absolute functions. Now we're going to deal with reciprocal functions, something a little bit different than absolute functions. And it's a change of pace. 2 lessons on reciprocal functions of straight lines, and then next day, reciprocal functions of quadratic equations of parabolas. And they both are funky looking. They're really both really cool. So page 184, let's jump right into this. We start off with a definition, and the definition is not going to mean too much to you until you start to jump in and try to figure things out. But if we have y equals f of x, then its reciprocal function is simply 1 over f of x. It's 1 divided by whatever the original function is, and that's how you get a reciprocal. And I think then that it'll probably just be easier to work through an example and then see if we can't sort out what this reciprocal function is, what this 1 over f of x actually means. So we'll do it by plotting a very simple graph and plotting its reciprocal. Let's start with the idea of this line called y equals x plus 1. We'll call that f of x, okay? And so I'm going to sketch that. What information do we need to sketch? I think we've got it all. It's got a slope of 1. It's got a y-intercept of plus 1. It's got a x-intercept of a negative 1. So it's going to look like this. All right, and just so we don't lose track of it, we'll make sure we know that this is f of x. All right, f of x. We probably can figure out the points by reading them off the graph. We've got the x values here, and so we're interested in what the corresponding y values are. Now we graph this by inspection because it's such a simple line and you've been doing these for so long that there's no real need to do a table of values. But let's do it anyways. So the way this works is if x equals negative 10, then y equals negative 10 plus 1 or negative 9. So we can do this all day long and get this done pretty quickly. Oh, oh, isn't that interesting? Now you may be asking yourself, where are we getting these funny numbers for x values? Negative 5 quarters, negative 4 thirds, negative 3 halves, and so on. I've got to admit that those are manufactured x points. Of course, we can use any value for x and find a corresponding y value, but we sort of are leading you down an introduction here. So we've carefully chosen those x values to kind of sort of make a point. So we've done f of x equals x plus 1. Let's do 1 over f of x, or 1 over x plus 1. And so we'll use a different color now. And the process looks pretty much the same. If x equals negative 10, then y equals 1 over negative 10 plus 1, or. And similarly, if x equals negative 5, then y equals 1 over negative 5 plus 1, or that. See, so what I'm doing is I'm plugging in the different x values into the equation, the 1 over f of x, and I'm just chomping out these results here for different y values. But I hope that you see that I can do this pretty mindlessly, can't I? Just by looking at what f of x was. What's the difference between f of x? Well, for every corresponding y value under f of x, 1 over f of x, or rather the y value for 1 over f of x, is just its reciprocal. It's whatever number you have flipped upside down. So 9 is really negative 9 over here is really negative 9 over 1, isn't it? And I'm just reversing those. And of course that should have been a negative. So I can keep on doing this without really thinking. All I have to look at is my x values. If I'm looking for the reciprocal of it, I just change by flipping it over. Now this is interesting. Negative 1. Well, if I plop or try to plop negative 1 into this 1 over f of x function, I get 1 over 1, negative 1 plus 1. In other words, 1 over 0. And what do you get whenever you divide anything by 0? You get that undefined And we're just going to say does not exist. Does not exist. Why? Because it is undefined. But we can go back on our own merry ways here, and calculating these numbers are actually fairly straightforward. Oh, look at that. No change. Interesting. All right. So there we have a table of values for 1 over f of x. And now it's no hard task to figure out the corresponding x and y values for a reciprocal function, but graphing it until you've seen these a few times is kind of interesting looking. So we know what f of x looks like. Let's try to graph 1 over f of x now. And what I'm going to do is I'm simply going to take these xy pairs here. So I'm going to take this and this. So the first one I'm going to look for is -10, -1/9. Now, those little fractions are really hard to estimate, but we can zoom in here and we can do our level best here. The next coordinate pairs I'm going to graph are -5, -1/4. Well, -1/4 is going to be sort of around here. All right, a little bit off the x-axis. And then I'm going to do -3, -1/2, which will be right around there. All right, so I'm going to go ahead and continue plotting the coordinate pairs of 1 over f of x, and I think we are at -2. So maybe you see what's happening here. When x is very negative, then the y value is slightly negative. And the graph keeps going without ever really hitting the x equals -1. And then at -9/10, something a little different happens. All right, let's continue here. I think we were at 0 and 1. All right, so it looks like as big as x is going to get, it's never going to give us a y value of 0. It just kisses down there. All right, let's see what this graph kind of looks like now. Closer and closer and closer to the x-axis. So there's an odd-looking graph. I don't think we've ever seen one like that. Welcome to the new topic in Math 20-1. It's a graph with weird, funky things called asymptotes. Don't giggle. This will kick you in the asymptote. All right. So there's our two graphs. Green for 1 over f of x and purple for f of x. It's time to identify some key features on this graph. So before we get too busy and carried away, let's do some labeling here. This is 1 over f of x, and so is this. And to be more specific, this is y equals 1 over x minus 1. Well, I want you to notice a couple things. I want you to notice that as x approaches -1, the y value is again really, really big here. But no matter what the x value is, the y value will get bigger and bigger and bigger, okay? But x looks like it'll never be equal to -1. That line approaches. And so I'm going to draw a line coming down here. The x value will approach -1 from the left side, but it'll never, ever, ever quite touch that. So we have a special name for something like that, and it's called vertical asymptote. Okay, vertical asymptote. And so that's a new feature of reciprocal functions, that presence of a vertical asymptote. All right, have you noticed that no matter what, the x value can never appear to equal 0? Well, there is another one for you, and we're going to call that the horizontal asymptote. And label that. So you've learned a couple of words here, asymptote. And if we take a look back at our table of values, maybe we can see what's going on here. Let's see what happens at at x equals -1. And you can see that when x equals -1, there is no corresponding y value in the reciprocal function. Okay, that's a unique feature of reciprocal functions. No corresponding y value at certain x values. So for y equals 0, you got to sort of look carefully and see what's going on here. Here's your y values here decreasing as x values increase, and you notice that 1/6 is less than 1/4 and 1/11 is less than 1/6. These y values are getting smaller and smaller and smaller as you go down. And I think you can imagine that as those fractions get smaller and smaller, they will approach 0, but you will never get a 0 out of them. So that's what creates the horizontal asymptote for you. Now, if we take a look at the graph, we can identify a couple of other unique points. Notice the 2 points where the f of x and 1 over f of x intersect, here and here. And notice for those 2 points where y equals plus or negative 1, here's y equals positive 1, and here's y equals negative 1. Notice that the equivalent values for f of x and 1 over f of x don't change. So those points that don't change, they have a name, and you've seen these before in the context of absolute values. Those are invariant points. And those are kind of important. This one here is 0, 1, and this one is -2, -1. So there we go. We have graphed our first reciprocal function, and there's a lot of information in there. And I think by understanding what's going on, by actually taking an example and just jumping right in, we get a better understanding. At least we start to build an understanding of what reciprocals look like and what they mean. So let's go back up to the definitions here and see if any of this doesn't make sense. If y equals f of x, and then its reciprocal function is y equals 1 over f of x, that is the very definition of a reciprocal. So if there's a point x and y on the graph of f of x, then that point will be transformed or translated into x comma 1 over y. All right. So notice that the x doesn't seem to change, but the y value does change. So let's see if we can go and summarize what each of those will be. I'm going to zoom down here and you can take a look at the graph while I do this. So the invariant points, just in this case, the invariant points are -2, -1, and 1, 0. The asymptotes in this particular example are at x equals -1 for what we call the vertical asymptote, y equals 0 for the horizontal, or HA. Domain, what's the domain going to look like? Domain is the values of x, so how far left and right. So the domain is going to be the values of x, such that x are members of the real numbers. And the only value that x cannot be is -1, and that comes from your asymptote. And your range, which are the values of y, such that, well, y is a member of the reals, and y can never equal 0. And in this case, if we want to state what are x and y intercepts, well, there are no x-intercepts in this particular case, and generally with most reciprocal functions you're going to deal with in Math 20-1. Next year that may change. And the y-intercept will be at 1, 0. So there we go. We summarized our first reciprocal function, a fairly easy one. It's all as simple as that. All right, so on the next page then, what we'll do is summarize our findings here and introduce some of the terminology a little bit more formally. An asymptote is a line that the graph approaches as x gets infinitely larger or small. Vertical asymptotes occur at a place you've heard about before. Those are the non-permissible values, which would allow for the function to blow up or become indeterminate or undefined. Any x value that would make a denominator equal 0 would be a vertical asymptote. Any x value that would make the radicand negative would be a non-permissible value. All that stuff you've just finished learning. The vertical asymptotes will occur at the x-intercepts. Notice I use plural there because there's only one x-intercept with a line, but there's more than one x-intercept with quadratics, which will be the next lesson and the final lesson of this sequence. So the VAs will occur at the x-intercepts of the original function because when y equals 0 in the original function, then y becomes 1 over 0 in the new. And any number divided by 0, of course, is undefined. As the x values approach the vertical asymptote, the y values grow without bound. That means they get larger and larger and larger. The y values go to positive and negative infinity. So that's the vertical asymptotes at the x-intercepts of the f of x function, which is to say that the vertical asymptotes of the reciprocals of f of x occur at the intercepts of f of x. Cool little trick to keep in your back pocket. Horizontal asymptotes, horizontal asymptotes. And now this is only going to apply for the work we're doing in 20-1 because next year things get a little bit complicated. But horizontal asymptote occurs when the x values of the function get increasingly large and the y values begin to converge to the value. So let's compare now the different domains and ranges and the behaviors at either end of the function graphs and so on between f of x and 1 over f of x. So let's call this f of x, and this would be 1 over f of x. Okay. So for f of x, the domain is just the x values that are members of the real number line. No restriction on x. But the reciprocal of f of x, 1 over f of x, would be values of x that are members of the reals, but x may not equal to -1. Because -1 would make the denominator of this 0, and 0 would make 1 over f of x indeterminate. All right, range. Well, typically the range of f of x, in terms of if f of x is x plus 1, y values such that y are members of the reals. Cool. And the range of the reciprocal of f of x would be all values of y that are part of the reals except for 0. Y cannot equal to 0. End behavior. What we mean by end behavior is what happens as x gets really, really big. So as x approaches infinity, what's going to happen to y? Well, in f of x, in the original function, y also approaches infinity. And as x approaches negative infinity, that is on the left side, guess what? Y also approaches negative infinity. Well, in the reciprocal function, as x approaches infinity, y now is going to approach 0. Never going to reach it, but it's going to approach it. And as x approaches negative infinity, y is also going to approach 0. What's the behavior of these two graphs at x equals -1? Well, at x equals -1 for f of x, you get an x-intercept. And for the reciprocal, you get a vertical asymptote. Invariant points. What are the invariant points on a graph? Well, in this case, for x plus 1, f of x equals x plus 1, the invariant points are invariant points. Invariant points are going to happen when y equals plus or minus 1. When y equals plus or minus 1. And that's going to be for both cases, when y equals plus or minus 1. For both the f of x and the reciprocal of f of x. That is the very definition of invariant points. They don't change after the function transformation. And what are those 2 points? Well, -2, -1 is the first one, and 0, +1 is the other one. So where y equals these 2 points, the corresponding x value gives you the coordinate pairs for the 2 invariant points, and that always happens. There is no vertical asymptote for f of x, but for the reciprocal at y equals 0. and there are no vertical asymptotes. I think I said horizontal asymptote a second ago. No vertical asymptotes either, but for the reciprocal at x equals -1. So there's a little bit of a summary, and I think we're ready to go and do us some more examples. So let's take a look at page 186. 186. Sketch the graph of y equals 1 over 3x plus 9 by first sketching the graph of y equals 3x plus 9. So right off, we know that that's f of x, and this is 1 over f of x, okay? The first one is the reciprocals of each other. So for this first example, we're going to do things a little bit longer than you need, just to lay out the steps and to give you a good outline of how to approach a question like this. The first thing I'm going to do is graph f of x. I'm going to graph y equals 3x plus 9. So for that graph of y equals 3x plus 9, we know a couple things. Let's just summarize them here. Let's make this step 1. For y equals 3x plus 9, we know we have a y-intercept of what? 0, 9. And we know we have a slope of 3. You can just read those two things off because we are in slope-intercept form already. A intercept of 0, 9 and a positive slope of 3. So 1 over 1, 2, 3 down. 1 over 1, 2, 3 down. 1 over 3 down. And all the way to the bottom here. All right. So what does this look like when I draw it? It's going to look something like this. Let's label it. F of x equals 3x plus 9. Well, our next step now will be to figure out, I think, our invariant points. So let's take a look at, see if we can figure out invariant points. So we know we get invariant points when y equals plus or minus 1. Okay, you can take that to the bank this year. Next year, things will change a little bit. It gets more complicated, but right now, invariant points are at y equals plus or minus 1. So for y equals positive 1, we're going to get, what we're doing is we're substituting y equals 1 into the original function right there, okay? So we're going to get 1 equals 3x plus 9. And if we move things around, we got -8 equals 3x, and x equal to -8/3. All right, there we go. Let's figure it out now for y equals -1. For y equals -1, we have -1 equals 3x plus 9. And when I move things around here, we're going to get -10 equals 3x, and x is equal to -10/3. Okay. So there are the two sets of invariant points. For y equals -1, it's -10/3, -1. And for y equals 1, it is -8/3, +1. There's your two invariant points. So we can go ahead and plop those into our graph over here. So here's -8/3, here's -3/3, -6/3, -9/3. So -8/3 is going to be around here somewhere, +1. And our other line is -10/3, -1. So here again is -9/3, -10/3 will be here, and -1 will put us there. Those are our two invariant points. So what that means is that when I take the reciprocal of the blue line, then the reciprocal is also going to go through those points like that. Okay, we don't know exactly what they're going to look like, but it's going to be sort of like that. We'll do a little bit better, but let's erase this and let's continue. We have just now picked our two invariant points. All right, so step number 3, let's do our vertical asymptote. And we're going to get our vertical asymptote when y equals 0. So a horizontal line. What's that going to look like? Well, that's going to be somewhere around here. So remember, asymptotes are values that are approached but which are never achieved. So the curved line is going to approach y equals 0, but it's never, ever, ever going to become y equals 0. Y can never equal to 0. Okay, next step. We did horizontal asymptote. Let's figure out our vertical asymptote. Now, our vertical asymptote is going to happen when the denominator of the function is 0. So here's the denominator of the reciprocal. 3x plus 9 cannot equal to 0, which if you rearrange things, x may not equal to negative 3. And there's our vertical asymptote. Let's go ahead and draw that in now. Perfect, good. All right, I think we've got everything here. We've got our asymptotes, we have our invariant points, and I think all that we need to do now is try to fit in a line. Remember, there's going to be two parts. Okay, there's going to be a part that goes like that, and another part that goes like that, okay? So, but we're going to draw these a little bit more carefully, starting with, let's do the top part of the graph here. If we wanted to, we could come up with some kind of ordered pair up in this way to really nail down how close. But for what we're doing right now, it is perfectly acceptable, seeing as how close that invariant point is to the asymptote is, just to estimate where it goes in. Now that green line should never be touching the orange, but when you're hand sketching on a tablet, it's going to happen. And on the left-hand side, looks like we've got a little bit more leeway here, approaching but never quite achieving x equals negative 3. All right, well, there's our two graphs. I think we pretty much done everything we want. Let's just check. We sketched the graph of 1 over f of x. We sketched f of x. Oh, state the domain, range, and the equations of the asymptotes. Okay, so let's just review here. Let's do a quick review right there. For the domain, and we're talking about the reciprocal, so 1 over 3x plus 9. The domain is going to be the set of x values such that x are always reals, no imaginary numbers here, and the only value that x may not be is negative 3. The range, well, the set of y values, y a member of the reals, why? Well, just because. And the only value that y may not be equal to is 0. Cool. It asks us to state the equations of the horizontal and vertical asymptotes. So horizontal asymptote at y equals 0, a horizontal line, obviously, along the x-axis, and the vertical asymptote at x equals negative 3, negative 3. Vertical line going through x equals negative 3. And now I do think we are done. We are done like dinner. Yep. All right. So we'll go ahead and do one more example of graphing f of x and 1 over f of x. It's reciprocal of a fairly simple equation. So we'll pop over to page 187 now, top of page 187, question 2. Show you now a bit of a streamlined version of what we need to do. We still need to do everything. We need to state the domain, the range, and the equations of the two asymptotes. Let us first graph f of x, okay? So let us define f of x equals x minus 5. And that tells us a few things right off the bat. We know that it has a slope of 1, and we know that it has a y-intercept at, not of, but at negative 5, which means that the y-intercept is 0, comma, negative 5. And so with much ease and simplicity, we can find negative 5 on the graph and draw a line with a slope of 1. All right, and off the charts it goes. Cool. All right, so there is f of x. Let's do invariant points now. Invariant points occur by definition for this year when y equals plus or minus 1. All right. So what that means is that we're going to take plus 1 and plop it into the original function here. Okay. And we'll also take negative 1 and plop it into that function, and we'll see what we get. Okay. So let's do y equals positive 1. When we do that, we're going to get 1 equals x minus 5. And I think you see quite clearly that that means that x is going to be equal to positive 6. So one of our invariant points is going to be 6 comma 1. And for our other invariant point, y equals negative 1, we'll simply plop negative 1 into the original f of x function. We're going to get x minus 5. And once again, you'll see pretty quickly that x equals 4 in this case. And so the invariant point, the second invariant point will be 4 comma 1. Right? So let's put those 2 points in here. Let's see where they are. So 6 comma 1 is going to be right there. And, oh, made a little mistake here. This should be negative 1, of course, because it's negative 1 up there. 4 comma negative 1 will put us right there. And a good thing that they both occur nicely on the graph. Okay, so we've got f of x, and we have the two invariant point plotted. Let's figure out, let's choose another color. Let's figure out, let's do a vertical asymptote. Let's figure out where the vertical asymptote is. All right, vertical asymptote is going to happen when x minus 5 equals 0. That is when that denominator equals 0, and that means that when x minus 5 equals 0, that is when the denominator of the reciprocal equals 0, which would cause for an indeterminate form or an undefined equation. So x minus 5 is 0, which means that x is going to be equal to 5. That is the vertical asymptote. And what's it going to look like? Well, it's going to be a line, vertical line, just like that. And what does that mean? It's going to be a vertical line at x equals plus 5. You can take a lot more care when you're drawing on your assignment page. Use a straight edge. Use the edge of your calculator to get a nice crisp line. I'm drawing freehand on a tablet, so mine is not going to look as good as yours are. And for our horizontal asymptote, well, it's always going to be, for this year, at y equals 0. Horizontal line along the x-axis. All right. So there we go. We've got enough information now to graph the reciprocal function. We know because of the invariant points that one half is going to be there and another half is going to be there. But all we need to do now is be able to draw it a little bit more carefully. So starting on the bottom left, it'll look something like this. And then the second part on the top right will look something like this. All right. Okay, that looks pretty good. Purple is the reciprocal, green is the regular function, and we are almost done. Let's see. We've got the formulas for the horizontal and the vertical asymptotes. So those are done. All that's left for us to do is to state the domain and range of the reciprocal function, which will look something like this. Values of x, members of the reals, and the only value of x that is not permitted is negative 5. And negative 5 is not permitted because, once again, of this denominator non-permitted value. Okay, if x were positive 5, then the denominator would be equal to 0. The whole equation would be undefined and it blows up. And finally, the range, values of y, y's member of the reals. And the only value that y is not allowed to be would be 0. All right. All right, there we go. Getting the hang of this. Not so hard when you're dealing with straight lines. They look really funny. You've never seen a graph like this before, but get used to it. We're going to be seeing lots more like this in our future. And finally, let us scroll down to question 3. Question 3. You know that we can do this. If we're given a equation, we can draw its curve and the curve of the reciprocal. But now we're given the graph, and we want to know what the equation of its reciprocal. The reciprocal of the reciprocal is the original function that gives us this shape here, right? So there is some f of x. We're going to call this This is 1 over f of x. There is some graph that looks something like that, which is the original f of x that gives us the reciprocal, which looks like that. Okay, so our job is to figure out this line right here. Okay, so let's erase this mess and work from a clean slate. How would I do this? How would I do this? Well, I would first look and see if I could figure out my invariant points, because I know that my f of x is going to go through those. Okay, and invariant points, remember, happen when y equals plus or minus 1. All right. Well, here is plus 1, y equals plus 1, and here is y equals negative 1. All right. So we could very easily find our two invariant points, and let's just state them. This the one on the left is 6 comma negative 1, and the one on the right is 8 comma positive 1. All right. So now we know the shape and the nature of the original line, the reciprocal of which you see here in black. So let's draw that line since we can. It's going to start somewhere around here and go up. Over 1, up 1, it looks like, because I go over 2, up 2. All right. So there is my original line. There's my original f of x. The question is asking us to, all it's asking us is to determine the equation of f of x. All right, well, we can do that. We need to know its slope. Well, we know the slope goes over 1, up 1, over 1, up 1. So we know the slope is positive, and positive 1. We know that. But just as a quick reminder, remember how we figure slope out formulaically? Y2 minus y1 over x2 minus x1. Remember that? So here's the two values there we can use. 1 minus negative 1 over 8 minus 6 equals 2 over 2, which equals 1. Yay, we have a slope of 1, but we knew that already. I'm just showing you and reminding you how we do that formulaically. Well, we know one form of the equation of a line that can be expressed as y equals mx plus b, where b is the y-intercept. Now, the y-intercept is down there, and I mean, you can suss it out. If this is 3 comma negative 4, then if I go 3 over and then 3 down, I'm going to be at minus 7. So we know that there's going to be a minus 7 intercept. But how would we figure that out algebraically? Okay? Well, it all comes back to this formula right here. We have a y value. In fact, we have two y values. We have 6 comma negative 1 and the 8 comma positive 1 up here. So we can plug either of these 2 points into y equals mx plus b to figure out algebraically what that b value is, and therefore what the y-intercept is. Well, let's use 6 comma 1. Okay, so negative 1. I'm substituting the y value in, equals m. M we know is 1, and x value is 6 plus b. Okay, we're trying to determine algebraically the b value. Well, what do we got? Negative 1 equals 6 plus b. B equals negative 7. Cool. So we could easily just logic out the slope, but I decided to do it algebraically up here. We could easily logic out the y-intercept, but we decided to algebraically figure it out there. It's asking us for the equation of the line. Here it is. Y equals mx. M is 1, so x minus 7. That's all it's asking for. And we are now done this penultimate lesson in this unit of study. Take a look at the notes underneath the video, and I will give you the page references and question numbers to work on. So go forth, math your little hearts out. Cheers.